talking more or less about one thing only, and that is area.
Yes.
And we have used rectangles to help us discover a few things about area. Last time we used trapezoids a little bit to help us discover some things about area. We try to be really general about it by using Riemann sums and those formulas that go into there. And then in 4.3 we said, you know what? We can actually have a shortcut for these Riemann sums, and it's called a definite integral. So it's a huge development. It makes our life a lot easier. In section 4.4, which will come next week, we'll learn a little bit about how you actually do the definite integral. It's really not that hard to do. You can subtract, and if you can find an antiderivative, you're good to go. It's really not that challenging to do mathematically, but conceptually, again, it's tough. All right, so we can use areas, too. We can use areas just like familiar formulas for area. So if f is piecewise and made with typically linear shapes like triangles and rectangles and squares, things that we know the area formulas of, then geometric area formulas could be the thing that makes this really, really easy. And you might look at this, I think it'd be pretty easy to look at this and say, wow, you know, this must not be anything that I would have to do. It's just too easy. Oh, believe it or not, even like we think way far ahead on an AP test, the thing we're about to do involving some really basic area formulas very well could be the thing that you need to do. Okay, it would be the best thing you could do. So I want to just give you a couple of examples here. The integral from -4 to -1, the integral from 1 to 2, so on and so forth, all of f of x. I think I want to start with the second one. So if you guys would, take a look at this one with me. The integral from 1 to 2 of f of x. This is a graph of f of x right here. And I actually have a few options that I could exercise here to figure out what this integral from 1 to 2 is. But in my opinion, the easiest way to handle this one would simply be to use area. Remember that the definite integral is going to be related to the area between the x-axis and the graph, right? So what I would do here with the second one is I would notice that the integral from 1 to 2 is really referencing this lovely geometric shape, that area, right? It's a triangle. How do you find the area of a triangle? Say again? So it's the integral from 1 to 2.
That would be -1 to 2.
I went too far. Sorry. You know what? Tim, I like your idea. Can we call that a typo? I don't know if that was a typo or not. Can we call that a typo and make it -1 to 2? Be a little more obvious. So let's fix that. So negative, I'll put this in red just so you can see a little bit easier. Let's call this -1 to 2. And that'll, I think, you know, that's probably what I intended because that's what I colored in there. Yeah. Okay, so now let me ask the question. What's the area formula for a triangle? Okay, wait again.
Wouldn't it go straight like all the way down too?
You said, that's, okay, so that's what a definite integral does. Remember, whenever we drew in like our Riemann sums, didn't we start on the x-axis and draw up or maybe down? That's where we start them. That's what a Riemann sum is. Because if you think about it, if all you did was say, hey, let's go ahead and calculate all this area, the answer for every single one of these would be, what's the point, right? So we know that would be the case. So we're going to use the fact that we want to stop at the x-axis to calculate interesting things. And that's why when people say, hey, let's find the area under a curve, I'm like, you know, that's not really what we're doing. We're finding the area between the x-axis and the curve, right? So it's a valid question for sure. Okay, let me get back to my original question. What's the area formula for a triangle? So here's all you would really have to do to figure out the value of this definite integral is say 1/2. What would be the base length? And what would be the height? I mean, I heard Kelsey say 4. Is everybody else with her? Okay, I just want to make sure we're good. And of course, 1/2 times 3 times 4 is 6. So there's a couple of ways we could describe our answer. We could say that the definite integral from -1 to 2 is 6. We could also say, if we wanted to, it's not what this asked us to do, we could also say that the area between the x-axis and the curve is 6, right? Both of those things would be true. Well, let's go back up to number 1, and I think you might notice an interesting point, which is brought up above. The point that I'm about to make is brought up in that paragraph above there. This first one says the integral from -4 to -1. So we are now, in this case, talking about this lovely purple region, right? Okay, so here's what you're going to discover. And you'll discover this that this naturally happens. We're going to make sure that we are careful with a situation like this. Wouldn't it be really easy to look at this and be like, hey, that's a triangle just like that red one. And if you look carefully, doesn't it have the exact same dimensions as that red triangle? Isn't the base length 3?
Mm-hmm.
And the height is 4?
Mm-hmm.
So you could easily look at this and say, hey, look at the area for that purple triangle is 12. Therefore, the integral from -4 to -1 must what am I saying? It's 6. It has been a crazy, crazy day.
Yeah, it has.
I'm going to blame my lack of arithmetic on that. There we go. Area is 6, right? So it would be really tempting to do this. Unfortunately, that would be incorrect. Let me explain why. The definite integral is a Riemann sum, right? And a Riemann sum is just going to be adding up a bunch of numbers. Okay? So I said this before, I'll say it again, I'll probably say it a lot. A definite integral is simply an infinite summation or an infinite accumulation of whatever you tell it to accumulate. Wouldn't you guys agree with me that all of the values through this purple region, all the values are negative? So when you're told, hey, I want to integrate or do a definite integral from -4 to -1, you're really being told, I want you to accumulate a bunch of negative values. So wouldn't the answer have to be negative? That only makes sense, doesn't it? And so the answer on this one would be -6. So up above, I throw this caution out and say, hey, this whole geometry thing is very useful, but be aware that when f falls below the x-axis, that integral from a to b will be negative. We're not saying that the area is negative because area is always non-negative, right? Area is 6 right there. But the definite integral is going to accumulate negatives and therefore give you a negative answer. Does that make sense? Area is useful, but you got to be careful. When the region you're talking about is below the x-axis, the answer better be negative, right? Yeah.
So on a test, if we were to have this, and we were to calculate the area, and then say since it was a definite integral, so it'd be negative, would that be okay?
Okay, so what did I ask you? What was the question?
To find a definite integral.
Okay, so let's say this was the question. Evaluate that, right?
Mm-hmm.
If you answer with anything other than -6, it's wrong.
So if you were to answer, and you had to justify it.
Okay.
Would you
That's a great question. I don't know that I would give you this type of information and ask you to justify it. I might say something like, and this would even be iffy, I might say show the work leading up to your answer. And that would just be make sure you show your little steps or whatever. But I don't think I'd ask you to justify that. I'm going to, like if you throw a -6 out there, I'm going to probably assume, hey, he found area or use some other method and made sure that the answer was negative. Yeah. Okay, so let's keep rolling here. Let me clear off the picture here. So let's say there was a different question. What if we looked at the third one, and the third one, of course, says, what is the definite integral from -4 to 2? So that means we would start accumulating right there, and we would stop accumulating there, and we'd work our way from left to right across the picture. Any guesses on what you think the answer would be there?
0.
The answer would be 0. Let's talk about why. As I move across my picture here and I start accumulating, everything I accumulate there would be a negative value, right? So as I go from -4 to -1, I would be accumulating -6. I'd be adding up and the end result would be -6. But then when I get over here to the -1, I would start accumulating positives. And we know from before that I'd accumulate a total of +6 on that interval. And remember, a definite integral is simply an infinite summation of these really skinny rectangles. So this should just end up being -6 plus 6. Of course, that's 0. Still doing okay? All right, and then the last definite integral here is the definite integral from -1 to 4. And I would like you guys to try that one on your own. Okay? So You've seen it. You've asked a few questions. I've talked about it a little bit. Now is your chance to try to do this one on your own. Walking around, talking with a few of you, I'm seeing some encouraging things. So the definite integral from -1 to 4, we would start accumulating right here at -1, and we would stop accumulating over there at 4. And so as I start accumulating, I'm going to think, all right, I'm going to accumulate moving from left to right across this. And I know from my earlier work that this ended up being an accumulation of +6. And then I get over here to this other part, which I have not done yet. And I see that this is also another triangle. And I calculate the area here. Did you guys get an area of 4? But of course, it's below the x-axis, and so the accumulation will be negative. So I would say that this would be a -4 accumulation. Therefore, the definite integral from -1 to 4 would be 6 plus -4. I'm coming up with 2. What do you think? Questions? Okay. So then the final question here, very conceptual. It says, what is the total area between f of x and the x-axis on the interval from -1 to 4? This phrase right here, total area, is really key. Right? I'm not asking you to find a definite integral of anything. I'm just asking you, what's the total area? What would you guys propose for an answer for that? 10 is right. Because you'd say the first area is 6, and the second area is 4. And somebody might protest and be like, no, the second area was -4. Remember, area, never negative. It's always going to be either 0 or positive, right? It's going to be non-negative. And so if we're asked for the total area, we're going to just take the areas for what they are, 6 and 4, and add them up. 6 plus 4, of course, is 10. That would be your total area. This concept of total area versus accumulating positives and negatives will be a recurring theme, for sure. Okay, so how do you feel? Are you okay graphically? Graphically definite integrals? Let's look at some properties then. This will just take a few minutes. I think a lot of these will be pretty intuitive for you. So let's look at these properties. And if you think about these in terms of area, I really genuinely hope these will make a lot of sense. I think they will. So if you look at the first one, it says the integral from A to A. So if you accumulate area from one number to itself, like from A to A, how much area do you think would be accumulated? That's right. And so if you ever see the integral from 4 to 4, or 2 to 2, or 1 to 1, or whatever to whatever, if the two limits on the integral are the same, then the resulting accumulation will be a big fat 0. Okay? And you might look at this and be like, when on earth is this ever going to happen? You'll see. It absolutely will. I really doubt you'd be asked a question like this, like, hey, number 1 on your quiz, what's the definite integral from 4 to 4? It won't be exactly in that context. It'll just show up when it shows up. And you want to be like, oh, that's 0. So just be ready for that to show up. Don't look at that and be like, that'll never happen. It will, for sure. Can I give you like a 12-question quiz and they're all that?
Yes.
Oh, it's 100%.
That goes straight into the test category.
0, 0, 0, 0, 0, 0. Done, and I did it in 20 seconds, and I got 100. All right. But you know if I did that, you would be like beyond nervous. You're like, what? What just happened? I must have messed something up because that shouldn't have been that easy. I don't want to cause you that stress. See, I'm looking out for you. That's really what it is. Okay. I'll just give you the real thing. So, anyway. All right, number 5. I'm going to give you just a really quick explanation on this. When we get into 4.4, you'll have a better understanding of why this is. So for now, if you have the integral from A to B, that's going to be equal to the opposite of the integral from B to A. So in other words, if you switch those limits around, you switch the sign. Again, that's an oversimplification of what's happening here. And in 4.4, we'll go a little bit deeper into why that is. But for now, if you switch those limits vertically, you switch the sign. And typically, it doesn't have to be this way. Typically, the A and the B have a relationship where A is the lower number numerically and B is the higher number numerically. That's what we get used to because we're used to accumulating from left to right. But you can always switch things around if need be. And if you do switch the limits, you switch the sign. So if you look at the example, do you see how the lower limit is not numerically lower? And so that means we're accumulating from right to left, and maybe we're uncomfortable with that, and I'm okay saying, yeah, I don't want to go from right to left. I'd rather go from left to right. All we'd have to do is say the opposite of the integral from 2 to 5. of f of x dx. And again, that seems really simplistic, I know, and you might think, man, that'll never matter. It will. It'll make your life much easier or much more difficult depending on if you do or don't do it. So consider. That make sense? For now? Okay. Let's take a look at a few others. Like number 6. I like this one. If you're thinking really well with areas, I think number 6 will make sense. It looks really scary. I mean, this long statement at the top here, that looks pretty scary. There's a lot of integrals and letters and f of x's and all that stuff up there. But here's the bottom line. Here's all it really means. If you have the integral from a to b, and you find whatever that area is, and then you have the integral from b to c, and once again, you figure out whatever that area is. If you wanted to know the full area from A to C, wouldn't you just take the purple area and the blue area and add them up? That's all this is really saying. It's saying that, I guess, this would be the blue area, and this would be the purple area. And if you want the full area, you just add the purple part to the blue part. In other words, you can split the integral up. You can put it back together. So in our example, really basic example down below, notice I've got the integral from 1 to 3 of f of x, and I'm adding to that the integral from 3 to 7. See how the 3's match? The 3's would bump up against each other. So how could I rewrite this in a simpler form?
1 to 7.
Integral from 1 to 7 of f of x dx. That would be equivalent to taking the two smaller areas and adding them up. You'd end up getting the total area there. If the graph looked like that, you could do it simpler with just the one integral instead of the two, perhaps. Make sense? Couple more, I think, and then we'll do an example. I think you'll get a chance to do an example or two, and then we'll be done. All right, so 2 more. Okay, so number 7. We've already sort of talked about this one. This is the constant multiple rule. So if you have the integral from a to b of k f of x, what you can do with that constant multiple is you can just get it out of the integrand, and then what you do, of course, you do what you got to do with the definite integral, and then you multiply the k back in. This is the same constant multiple rule we looked at way back at the start. So in our example down here, what would we need to do to illustrate that property? Yeah, get the 7 out. So the 7 comes out, and we get this, and then we have no idea what f of x is, so we'd need a graph or a function for that or whatever, and then we do what we got to do, and then you multiply the 7 back in afterwards. The 7 is not disappearing, it's just being put on hold, and we deal with it later. And then number 8, the last one here, is also potentially very, very useful. The definite integral of a sum, just like we talked about before, is equal to the sum of the individual definite integrals. So I could say that it's the integral of f plus or minus g. I could say it's the integral from a to b of f of x dx plus the integral from a to b, or plus or minus, I should say, the integral from a to b of g of x dx. So in other words, you can go term by term by term. We've been doing this, so this is not particularly new, but it's just an old property that applies to definite integrals as well as those indefinite integrals we did before. And I think this will be particularly useful in this example. So if I was going to try to use that property to help me split this up, any ideas on what it would look like? What do you want to verbalize?
Would you want to use the constant multiple rule for...
So here's what's interesting. I was wondering if somebody's going to say that. Here is a potential pitfall of the constant multiple rule that if you did use the rule we're talking about now, you'd be able to get around that, right? So if you did this, like what if somebody looked here and they said, hey, the 5, that's a constant multiple, isn't it? And they said, you know what, I would like to get this out, and they did this. Haven't they just committed a mistake? Do you see how by pulling the 5 out, they've now mistakenly applied it to both pieces of the integrand, right?
Apply it to one?
Not the way it's written.
But if you were to...
What do you mean
when
if
you
you
separate it, can't you?
Now, after you separate it, you
Yeah,
can.
that's what I
Yes. Okay, yeah. I didn't know if you meant to do it at the start or the end. But the point you bring up, though, Tim, is the usefulness of both rules. So, again, what would it look like if we just split it up? Can anybody verbalize? Integral from 3 to 4 of
X to the fifth
dx.
Plus integral, the 5 is in the
Very good, very good. Okay, so this would be simply splitting it up. I heard you all in concert. It was impressive. That's simply splitting it up. And then Tim's idea of, well, wait a minute, couldn't we get the 5 out of that second integrand? We sure could. And so, that maybe would be a second move here. And you say, all right, well, then really, to get this all the way as simple as we maybe would want, I'd get the 5 out, and it would look like this. And once we get a little bit into section 4.4, this would be a pretty easy one for you guys to do.
If we're on a quiz and we have a problem like this,
Yep.
do we need to take the 5 out in order to get full credit, or is that?
Well, so I don't know that I would ever ask you to do exactly what we just did. I wanted to illustrate those, but in the course of like the examples we're about to do, that skill could come into play.
Okay.
In fact, it for sure at some point will. So let's look. Maybe you'll get an example of what this might look like. So take a look at what we got coming up. I think there's 2 of them. Yep. So for the following examples, use those values for those definite integrals. You're just told that. We just have to say, okay, cool, those all equal, whatever they equal. And then in number 9, what we're supposed to do is evaluate that expression. And then number 10, again, using the same values, evaluate that expression. You should have to use some of the properties that we just talked about. Okay? So let's see if you can apply them. Feel free to flip back and forth and discuss. And obviously this is relatively new, and so don't feel like you need to be perfect at it and just be solo. You can talk, you can ask questions. So take a few minutes and do this. Ready, go. Okay. And so I'm thinking, well, the 2, I might not know everything that I need to do here, but I could at least get the 2 out, right? That would be a start. So maybe I write that. I say 2 times the definite integral from -2 to 9 of f of x dx plus, well, and then, the fact that you're writing down is going to get you moving. And maybe you get to this next one and you're like, well, hold on. Integral from 7 to 3? That's backwards from the way I'm used to it. So why don't we switch those around? And instead of 7 to 3, we go 3 to 7. But we can't just switch those around unless we also switch the sign from a positive to a negative. So that's what I'm going to do. Make this from a positive into a negative. My point simply being that if you don't know what to do, but maybe you know like a little tiny thing about what to do the little tiny thing and get momentum going, right? Get movement started, and maybe that'll get you going in the right direction. So now I look at this and I'm like, well, shoot, the integral from 3 to 7 is 10. So this is just minus 10, right? I can replace that whole definite integral with 10. But then I can see how someone would get stuck on the first part still, right? Because there is no integral from -2 to 9 of f listed up above. What is there that might help us? Yeah, and notice how the 5s butt up against each other. And so this is that additive area idea where you can add up this little area and this other little area and get the whole thing. So this would really be 2 times 4 plus -12, right? We're just going to add those 2 individual integral values up, and now I'm just down to arithmetic, right? So this would be 2 times -8, that's -16, minus 10. I got -26. What do you think? We're dealing with kind of some abstract ideas with areas and properties. Max?
On the 5 to 9 one, the fx doesn't have a dx after that? Is that...
That's that's just a typo.
Okay.
Wait, what are you talking about, Max? There's a dx there.
On mine.
I'm just messing. I just wrote it in there. Sorry, that's a typo. And that, Max, is a good question because, believe it or not, if that dx is or isn't there, radically changes the meaning of what we're doing.
Okay.
The dx really should be there.
Got it.
Okay. So then, number 10. Did you notice on number 10 there was 2 different constant multiples? There was the 3 and the 4. And so we should probably get both of those out. So it'd be -3 times the integral from -2 to 5 of f of x dx plus 4 times the integral from 3 to 7 of g of x dx. The limits of integration agree, right? We're accumulating from left to right. So the integral from -2 to 5 is 4. So it'd be -3 times 4 plus 4 times the definite interval from 3 to 7 is 10. So that's negative 12 plus 40. I got 28 for that. Okay. Dan.
Like on a test or something, are you allowed to do that in your head? Just do like negative 12 plus 40? and then
Sure.
just-
Oh, yeah, totally. Absolutely. And depending on how big the numbers are, I probably maybe even put this on the calculator active section. There'd be no real advantage using a calculator other than just the arithmetic that you could do. So, okay. Any other questions, concerns, comments? So let me just sum this up for you guys. The last week has been about area, and today has more or less continued to be about area. The only thing left to be said here, guys, the only thing left to be said is, well, we learned how to do this from a graph. We learned how to do this from a table. We learned how to do this using properties and kind of a verbal expression. How do we do this analytically? How do we actually do this when we have the rule for the function? Make sense? So let me just give you a brief preview of that. We do have an intro video for next week sometime. It's like next Wednesday or whenever. You look on the calendar. I'll remind you. It's how do I do stuff like number 1? How do I do stuff like number 2? How do I do stuff like number 3? And let me give you a hint. If you know how to do antiderivatives and you know how to subtract, not kidding, you're good to go. Okay? If you know how to do an antiderivative and you know how to subtract, the rest of the details should work themselves out just fine. Okay? That's it. So